All right. Welcome everyone to this webinar hosted by Toradex entitled Bringing Displays to Life, MIPI DSI Driver Development for Linux. My name is Colin Boss and I am a field application engineer at Toradex. Let me also introduce you to our main presenter for the day. With us today is Stefan Eichenberger. He is an accomplished embedded software developer from the canton of Bern in Switzerland with his own company, Embear. So before diving into the webinar, let me cover a few organizational points first. Please use the chat window of the webinar tool if you have any technical issues and wish to let us know. At the end, we will also do an interactive question and answer session. You can type your questions in the chat window anytime you like, and we will pick them up by the end of the presentation. The webinar will be recorded and made available for on-demand viewing. With that being said, let's get started. So, Toradex, what we do. We do ARM-based system on modules, which are reliable with long-term maintenance, scalable, and available from stock. For the use of system on modules, we provide industrial-grade SBCs with included fully integrated software support and a general long-term support from prototypes up to volume. In order to accelerate development, Toradex can provide both custom solutions as well as off-the-shelf ones. This includes enclosures and accessories for applications such as industrial PCs, HMIs, and Edge Gateway. Finally, we provide full-scale software stack for OTA, remote updates, cybersecurity topics such as the EU CRA, secure offline updates, and device monitoring, as well as remote access itself. This all aims to reduce maintenance costs to our customers, but more on Torizon a little later. Toradex has been in the market for over 20 years, and we have more than 3,000 active customers from all over the world. Our customers are supported by 8 global offices, and in addition to that, we also have a network of over 70 proven partners. With our ARM-based system on modules, or SOMs in short, Toradex offers a multitude of beneficial factors from our global offices. And they include, for example, pin-compatible SOM families, the in-house hardware and software development, a 10+ year product lifecycle, free product support, direct sales, and global reach with the said local offices. I would like to mention a few milestones that Toradex has reached as a market-leading embedded soft and hardware developer, and they are shown in this slide. Things to point out are, for example, our breakthrough in 2005 with the Colibri family, which is still available to this very day. Furthermore, the release of Torizon and its cloud services, as well as the steady release of new product families such as Verdin and our flagship Aquila, are noteworthy. Nowadays, we offer modules with both NXP as well as Texas Instruments SOCs on them. I'd also like to explain our focus applications. We are optimizing our products and offerings for them. So that would include, for example, healthcare, industrial automation and robotics, transportation and agriculture, test and measurement, smart city, artificial intelligence, and computer vision. Typical projects are customers with volume requirements of a few hundreds to a few 10,000 products per year. And Toradex itself has thousands of active customers at the moment. Here's a short overview of our products. We have 5 SOM families inside these families, and the modules are pin compatible itself within the family. So you can, for example, seamlessly scale from IMX6 over IMX7 to the IMX8 within the same family. We are also providing production quality software with these modules, but you will learn a bit about that later on. Here we go. So this is Torizon. Apart from a highly reliable system on module, Toradex also provides production-ready software, including reference images for the Yocto project, and Toradex is also active in mainlining code for its system on modules. So Torizon is a brand new free offering from Toradex. It's an open source and easy to install Linux platform. It focuses on lowering your time to market and can be used out of the box. So it's based on open software, and you have no lock-in, and you can adjust it to your own needs and requirements. And Torizon comes with automotive-grade update client to allow for simple, safe, and secure software updates. As an example, software updates are safe even if you lose power in the worst possible or imaginable moment. Security is another focus, so frequent updates and simple access to hardware, security features that make it easy for you to develop a secure device. So that would conclude our short introduction into Toradex, and I would like to hand over the word to Stefan Eichenberger.
Thanks a lot, Colin. So now I would like to come to the little bit more practical part and talking about MIPI DSI driver development for Linux. So first of all, what are MIPI DSI displays? So we will talk about displays. But if you think a display is just what you have in front of you, like a monitor with HDMI cable, that's not really true for embedded devices. So embedded devices normally have displays which are more focusing on a specific use case. So it doesn't support different resolutions, and it also has different form factors, as you can see in these pictures, things like square displays or long displays, depending on your application. And this is where we're focusing now. This brings me already to a question to you. We have something called polls, and I would like to ask you, do you already use embedded displays in your product, or is this something you didn't do so far? So you should soon see a poll coming up.
All right, so this is indeed the poll you should be seeing now with the question, do you already use embedded displays in your products? And the selection is yes, we already use MIPI DSI. Yes, we use LVDS parallel RGB. Yes, we use HDMI, DVI, or VGA. And then the final two answers are either no, but we plan to use one in the future, or no. And I can already see that there's quite a lot of our attendees voting. And I'll be quick to share the answers. So as we can see, most of our attendees, so about a third, have clicked on yes, we use LVDS parallel RGB, and 30% are already using MIPI DSI. And then equal parts are either using another interface or they're planning on using one in the future, and only 5% are saying no. So thank you very much for participating on the poll.
Okay, that's great to hear. So yeah, some of you even use MIPI DSI displays, and I think especially people coming from the parallel RGB world or LVDS world, this talk might be interesting, because especially newer SoCs often only support MIPI DSI, or they tend to switch to MIPI DSI. So that's definitely something that could be interesting for you. So when we talk about display interfaces in the poll, we already saw there are things like parallel RGB. This is basically where everything started for embedded displays. Parallel RGB, the idea there is just you have for each bit of the color. So if you have 24 bits, 8 bits per color, you have 24 data lines from the SOC going to the display. And then additionally, you have a pixel clock, which basically tells the display when the color should be applied to the display. This is for the hardware guys normally a little bit of pain because they need to lay out that properly and they have to waste a lot of space. That's why then soon something better or different came up, that is LVDS. LVDS has a different advantage. Instead of transferring the data with TTL logic, it uses differential signals that also lowers the emissions so that you more easily pass EMC tests. And the same idea more or less applies for MIPI DSI and also for DVI, but DVI we don't talk about it. It's the protocol used, for example, when you use an old DVI cable or also HDMI, which tunnels DVI through HDMI. So why do we need another protocol if we already had LVDS? So as said, newer SOCs tend to use MIPI DSI, and the reason for it is the bandwidth. So LVDS with 4 lanes, for example, on an IMX8M Plus supports up to 2 gigabits per second. This is enough for full HD display at 30 frames per second. However, if you need a 4K display or a display with 60 Hertz, then you already are at the limit, and then you would need dual channel LVDS, so that would again double the data signals. While in comparison, MIPI DSI already with the first version supported 2.5 gigabit per lane, so 1 lane compared to 4 lanes. So if you would have 4 lanes, you would even have 4 times that speed. So it's even possible to transfer the display data of a full HD display over 1 MIPI DSI lane at 30 frames per second. Additionally, what they introduced is an uplink and a downlink on the first MIPI DSI lane that allows you to send data to the display or to the display controller. What that means, we will see here and on that slide. So to understand how we have to develop a MIPI DSI driver, we need a little bit of the background about the whole Linux display framework, which is called DRM. And how it works is you have a frame buffer that's normally the background, and the background can also be your whole application. If you, for example, use Qt with EGLFS, that would draw your image to the frame buffer, the background. Then you have several planes like cursor, or you can have an overlay with a video, and the CRTC, which is a hardware controller, then takes care of fusing them together and creating one image out of it. This image is then fed into an encoder. The encoder makes from this memory that is output by the CRTC some timing information. So it adds the pixel clock, and then it outputs the pixel data at the right time. This one could already be fed to a display. So if you have a parallel display, often the encoder is then connected to a display directly. However, with MIPI DSI, what you often see is that they internally have then a bridge, a MIPI DSI bridge, so that bridges the data from parallel RGB to MIPI DSI, kind of serializing it in the right way for MIPI DSI. And it sends this data then to the display controller. Most MIPI DSI displays have a display controller. The display controller is responsible to prepare the data that it receives on the interface for the display. So if it's an OLED display, it prepares it for the OLED display, but it can also just convert it back to parallel RGB if it's a parallel RGB display. What we have to do to make a MIPI DSI panel work or the MIPI DSI display work, we have to write the MIPI DSI panel driver. And this panel driver contains the information about the timing for the display. So what pixel clock we have, what resolution we have, but it also contains things like init sequence. So it sends basically some data to the display controller that will set values inside this controller. That's the uplink that we have now with MIPI DSI. It can, for example, be turn on the display, or it can be set the brightness to full or to half, and so on.
I would have a quick question here.
Yes.
So is there any standard connector for the MIPI DSI displays, or is it more just pick and place?
Yeah, that's unfortunately there is no interface or standardized interface. So every display has a little bit a different connector. It also has even the physical connector is different. For the Toradex modules, they decided to use for the most carrier boards the same connector and also the pinout. So between the development boards, you can swap them. But unfortunately, there is no standard connector available. So it's only the protocol which is standardized, but not the connector.
Okay, thank you.
No problem. Yeah, then something else we need to understand is the display characteristics. The display characteristics is timing information for the display. So when you are familiar with LVDS displays or parallel RGB displays, you normally define that in the device tree. You set a pixel frequency, then you define the active area where your image is shown. So that's the time when actually data is shown on the display. And then you have some port values. This was back in the days when you had the CRTC monitors. It was basically when the ray was not visible, and then you also had the sync, and the sync was when the ray was traveling from right to left. This is nowadays still there for newer displays. It's also there for LCD, it's even for OLED displays. With MIPI DSI, or MIPI DSI allows you to transfer data during these port phases. So that's also the upstream to the display can basically be transferred during the port times, so that you can in real time reconfigure the display brightness, for example, or turn off the display if necessary. Then from the manufacturer of the display, you need some documents, because without them you will not be able to write the driver. So you need to ask them for the detailed data sheet that contains the timing information, it contains the timeout, and often you have more than one data sheet. So you have the kind of product placement data sheet, which just tells you how good the display is. But then you also have another data sheet that you have to really request from them, and there you find more information about the timing. For MIPI DSI displays, you also need init sequence. So this init sequence, as said, is something you transfer to the display controller. Can be also things like gamma correction, so that the colors behave correctly. This is something the display manufacturer has to provide you. And they often include that in the data sheet, or then as a separate file with pseudocode. Here is an example of a data sheet. Here you can directly read out the timing values, so the active area, then the port values, and the sync values. This is not always that clear. So this is, in my opinion, quite a good data sheet for that. There are some where they poorly talk about it. then normally the active area you really know, but the porches and the sync values are sometimes a bit unclear. You can also try out a few different values and maybe you figure out their working values, because they don't have to be exact, precise or on one pixel. You have a little bit a margin. We take these timing values and put them in a table. Then if the pixel clock is not defined by the data sheet, we can calculate it. So if you want to have it at 32 Hertz, for example, as in this scenario, we just sum up the horizontal and the vertical timings, multiply it, and this gives us the pixel clock, which is 70 megahertz for this display.
I have a quick question here.
Yes.
Sorry for interrupting. Is the MIPI DSI data transfer also used to transfer the touchscreen data, for example?
No, the touchscreen data cannot be transferred through the DSI, or maybe it could be transferred through the DSI protocol, but normally you use something different like I2C, because the touch panel is normally independent of the display itself. So it's just an additional layer you put on top of the display. So normally you don't have that embedded in the MIPI DSI protocol.
Okay, thank you.
Yeah, from the what you can see in the datasheet as well is the init sequence. So here an example of that. So you have some numbers. They are in the MIPI DSI standards. They are called commands. Here they call it addresses, but it's the same. So you have a command, and then you have some payload you have to send to the display. If you don't have the datasheet of the display controller, you don't know what they mean, because they are not standardized. There are a few which are standardized, like sleep out, display on. These are standard MIPI DSI commands, but for a lot of them are just vendor specific. And also the payload, it's not necessarily only 1 byte, it can be more. They can, I think, go up to 1000 bytes or so. So it's not limited to 1 byte. So now that we have all the data, we can start with implementing the Linux driver. As earlier showed, the panel drivers are part of the Linux DRM framework. So the panel DRM framework is the currently used display framework for Linux. It implements all the display controllers, it implements GPU drivers, but also panel drivers. Before you had the frame buffer framework, but that is deprecated, so just focus on the panel drivers. The examples I show you here are available on GitHub. At the end, you can find a QR code you can scan to my webpage. There I also list the GitHub repo. Yeah, so this will bring me to the next poll, and that is, are you already familiar with Linux driver and device trees? Because now we will dig into these topics.
All right, by now the poll should pull up on your screen with, as said, the question, are you familiar with Linux drivers and device trees? And the selectable options are, I develop Linux drivers on a daily basis. The second one, I already wrote a Linux driver and I know about device tree. Third one being, I'm familiar with device trees, but haven't written a driver. The fourth, no, I'm not familiar. I just want to make my display work. And the last one being no. Can already see that a lot of attendees have voted. And at the moment, most seem to go for the third option. I'm familiar with device trees, but haven't written a driver. And that would conclude it. So looking at the results, only 1% of the attendees said that they develop Linux drivers on a daily basis. Most of the attendees at 44% said, I'm familiar with device trees, but haven't written a driver. Then a bit more than a third said, I already wrote a Linux driver and I know about device tree. And then A few at 13% said no, not familiar, and they just want to get their display to work. And finally, 4% said no. Thank you for attending.
Yeah, thanks a lot. I think that's quite good. I think people already or writing drivers on a daily basis might be bored a bit, but if you are familiar with device trees but haven't written a driver, I hope this talk will really show you some ideas how you can make your display work. So how does a driver look like? Because unfortunately we need to write the driver because of this init sequence. There is currently no generic way how we could put this init sequence into the device tree. So a driver normally looks like this. So you have a macro that defines your driver and makes sure that the driver registers in the Linux kernel. So in this macro hides some register function or init functions basically. But in the end, it registers this structure here in the Linux kernel. The Linux kernel will then parse the device tree, and if it finds a compatibility for your panel that matches, then it will probe the driver. So it basically just checks, do we have a MIPI DSI panel that matches company my panel in the device tree? If so, then it will probe it and it adds this payload. We can see here this template descriptor, so that we can have the same driver, but we support multiple displays, for example, with a different resolution or with a slightly different init sequence. So what do we have to fill in there? So this template descriptor, this can be any data that we, or at a structure that we defined. So for this structure, we just have a mode. This mode will contain the timing information. Then it contains how many MIPI DSI lines we want to use. It contains the flags in which MIPI DSI mode we want to use the driver basically, and the format, which is just 24-bit, the color format, and then the init sequence. So the init sequence is a function. Regarding the modes, MIPI DSI knows a lot of different modes, like video mode, command mode, then for video mode, different sub modes, and ST made a really good application note about that. I put the link in here. Yeah, check this out, because it's quite hard to go into detail here. Just one thing, often you just need the video mode. You need to add the MIPI DSI mode LPM so that you can transmit data during these port phases. And the other ones, maybe you find them in the data sheet, maybe not, but with a little bit of understanding, you might figure out which ones you have to set. Normally, these two you should set. So, because the command, so yeah, maybe not something to the command mode. The command mode, which would, if you would omit this video mode, is basically when you just send data, but that would require the display controller to have an internal frame buffer, and then you send the display content in the command mode and fill in the internal memory of the frame of the display controller, and that will then drive the display. But this is not supported by all drivers. It's also not supported by all controllers. So for example, the IMX8M Mini supports it, but the IMX8M Plus doesn't support it, even though they use almost the same infrastructure. So it's, yeah, the video mode normally is the one you want to use.
Right, okay. So maybe a bit of a different question, but about splash screen from U-boot to Linux with MIPI DSI. Is that possible to show that?
Yeah, you could also try to show the splash screen in U-boot. However, that highly depends on the SOC, and normally it's not really supported by Toradex as far as I know, because a lot of socks don't support it properly. So ideally try to show the splash screen earliest in the Linux kernel. That's normally easier.
Okay, yeah, thank you.
So yeah, so the other thing we need to fill out is the mode. So that's also from the structure I showed before. The mode now contains our timing information. So the table I showed you before that we got from the data sheet. So we take the timing, the display clock, and add that to the mode, and that's it. So it's more or less a one-to-one copying from the table to the actual driver. What we also have to tell is the type. So mode type driver means that the mode is defined by the driver, not that you cannot change it in the user space or set it in the user space. The other thing is that the preferred mode, because embedded displays normally only have one mode. When you look at the HDMI displays, they have several modes. One is the native mode, that would be the preferred one, and then you have some upscaling that can be done on the display. And yeah, you can also set some flags to drive the VSync signal if it's active low or active high. That's just through the flags. Hopefully you find this information in the data sheet. Or if not, you can just try to play with these values. Then yeah, the init sequence that looks as follows. So you would put in the init sequence in here. That's basically one-to-one from this table I showed before. What is a bit special about this display is, or in the datasheet they did not tell that, so I really had to get to the display controller datasheet, which is normally something you need to sign an NDA with the company that makes the display controller, which is unfortunate. But what you figure out in that is that you can also switch to video mode, because by default it is in command mode. So you would have to fill the frame buffer, and then the display controller is driving the display. This is what I told before. But it allows you to switch to video mode, but that you can all figure out if you have the display controller datasheet. And you also have to turn on the backlight. So here it's at full brightness. The reason for that is that normally it's just black, and they also didn't document that in the datasheet. So this is also something that you have to figure out from the controller datasheet, unfortunately, or then you really have to make pressure to the display manufacturer to get the information. One thing I show here is you can also read back values if what you want to debug. I will also show that later on. It's possible to read back data through the downlink of MIPI DSI. Yeah, then this should not be too surprising. You just need to add the panel driver to your kconfig file so that you can select it when you type make menu config, for example, so that you can enable the driver. And then you also have to tell in the make file what it has to compile. So when you select, so if you enable the driver, then with that it knows, oh, I have to compile this C file to an object file. That's it. So that's the whole idea of the driver. But I normally recommend try to make sure that you really can iterate fast. So because at least for me, it never works just from the beginning. I have to do some adaptations, and there it helps when you can iterate fast. So this is normally how it looks like when I try it. I just try to compile the driver standalone without anything else, then copy it to the target, and then I do a reboot, and within 30 seconds I should know if the change did something, if it's to the better or to the worse, something like that. Some remarks, the downstream NXP kernel. So I was not showing that, but you have a prepare and an enable function where basically the init sequence is called, that I showed above. This you will see in the sample driver, so no worries if you have a look at it. I just didn't want to talk about it because it's a little bit boring. But there is a prepare function or an enable function, and unfortunately the downstream NXP kernel does not support sending MIPI DSI data in the prepare function. It only allows it to do it in the enable function. However, all upstream drivers send it during the prepare functions. So if you use an upstream panel driver, if you find one, then you would have to modify it slightly so that it sends the init sequence only in the enable phase. That's a bit unfortunately, but yeah, this is how it is. Yeah, then yeah, again, the example driver is available on GitHub. And now that we have a driver, we need to make the kernel know about it, and that's how we do it in the, or what you have to do in the device tree. So I think most of you are at least a bit familiar with that, so that's awesome. So yeah, we now create the device tree or the device tree overlay. It's not that important if you choose to directly edit the device tree or add an overlay. It looks like more or less exactly the same. So what you do is you have the MIPI DSI node that you want to modify. So you add here a panel. It has to be part of the MIPI DSI node because we made a MIPI DSI panel driver. So the MIPI DSI panel driver, if we look again at what we did here, so it's a module MIPI DSI driver. That means it needs to be part of a MIPI DSI node, else it will not probe. And this is basically what we do here. So we say we have a panel, we say our compatible, then we have a reset pin, and we have to define a remote endpoint so that we can connect the panel with the output of the bridge. So this port here is basically the data that goes out of the MIPI DSI bridge, and we feed that into our panel and vice versa. So they're just connected. That's how it looks like for upstream kernel. For downstream, NXP decided, why should we do it like that? Why do we need this connection here? So you don't have to do it there. And if you do it, it will not work. So that's an important point. Yeah, unfortunately, this is how NXP decided to do things. I think for TI, it's anyways a bit different. So yeah, no worries about that. And you can also see this wait until enabled flag here. That's because, as said here, the MIPI DSI or the downstream kernel does not allow you to send data during the prepare function. So that's why it is done in the enable function. That's something I solved in the device tree there. Yeah. Then again, for the device tree, make sure you can iterate fast, because even the device tree, even if it looks simple, often it requires some iterations. For me, the workflow looks as follow. I make the device tree, transfer it, reboot, and then again within 30 seconds I know if the change worked or if it didn't. Okay, then now it is time to show some videos of a potential bring up. I hope this works. Okay, the first video will show an issue with the horizontal sync. So I made the timing for the horizontal sync too small, and what you see is you see some flickering. So you can see at the edge this slight flickering. I will play it. It's the horizontal perch, even though it looks like it's the vertical one. I rotate the screen, so that's why it's a bit confusing, but just it's not 1920 times 1080. It's 1080 times 1920. So just that for it, why it is basically flipped. And then the next video will show an issue with the VSync. So when it's HSync, normally you will see a strange effect in the horizontal direction. With VSync, you see it more over the whole picture, but it's not always the same. You cannot say if it's that for every display it looks the same. Sometimes it can really have strange effect. It can just have some offsets and so on. So I will play. So here you can now see, I play it again. It flickers the whole display, but you can see it's kind of something with the vertical timing is not good. That's why it goes over the whole display. And the next video is showing if I overclock the pixel, I set a too high pixel. So it looks kind of stable, but of course you cannot see anything. Just yeah, I think this is because my layouting skills are not that good, and I made probably not the layout has some bad EMC effect. That's why when I try to use more than 32 frames per second, the display behaves like that. And the last thing I show is the video as we expect. Here you can see it's now really stable at 32 frames per second. So yep, now that we have the display running, we maybe want to move it to Torizon. For that, we use the Torizon Core Builder. I also made an example project that you can just use together with the sample module. I would like to ask again, are you familiar with the Torizon Core Builder? So did you hear about it or maybe already use it? That would be our next poll.
All right, so the poll should show up again on your screen with the question, are you familiar with Torizon Core Builder? And you can select out of 4 choices, the first being yes, I use it on a daily basis, then yes, I've already used it, yes, I've heard of it, but I haven't used it so far, or no, it's the first time hearing of it. So I'll give you a few more seconds to vote. I can see most of you have already voted, and I believe then we can have a look at the results. All right, so 0% have said they use it on a daily basis. 1% has said yes, I've already used it. 38% have said yes, I've heard of it, but I haven't used it so far. And 61% have said no, it's the first time hearing of it. So that's a little surprising.
Okay, yeah, so then I maybe should say a few words about it. So this is a tool from Toradex that allows you to customize the Torizon distribution. So it allows you to add device trees or additional kernel modules to an already existing image that was compiled by Toradex, which can be nice because then you don't have to rebuild everything yourself with Yocto. How it looks like is you have a YAML file where you then add some customization. Here you can see I'm adding an overlay and I'm adding a kernel module. In the kernel module, I just copy the one from before to my folder and then add a make file, and that's it. So then from then on, it should be able to compile with Torizon Core Builder. Now that we have that, I can just build the new image and then deploy it to the target and reboot it automatically. So this is how the flow looks like. I build it and then I deploy it. This looks much easier. It is also easier in handling it because you don't have to compile the kernel yourself. You don't have to care about the correct version, the correct kernel configuration. So it is easier. However, it's also a little bit less flexible because you cannot debug kernel drivers. So that's why I prefer normally to work first with the kernel driver or the kernel directly and make it work there, and then move to Torizon Core. So yeah, that would bring me to the next video. Here you can then see the whole flow. So one thing is the commands. So this is then how it looks like. This is just, I forgot to unmute.
Yeah.
This is the thing. So you basically get the kernel modules, then you call build. So this is the Torizon core builder build. It will compile the kernel module, it will compile the device tree overlay, and then repack everything. And now we can deploy it. That's with this Torizon core builder command, and say also that it should reboot. Now, if we are on the target, we will should soon see the message that it now reboots. And yeah, we can see U-boot, and now we have the changes applied that we have included in our customization. You can see here it tries to bind the bridge. If you see errors with -570, don't be worried, that's normal. That's just a deferral message. So it says I have to defer because I cannot find the module, and then it later tries it again. And the last thing I do, I just show an image on the display to have something there. So that's it. This is then how it looks like when we see the target booting. So yeah, that's the module with a word in and connected to my display. You will now see a short flickering. This flickering just happens because by default you have a random. I will play it again. You see a short flickering, and that happens because when it starts, the frame buffer is filled with random data, and it will output this one to the display. You could avoid that by just enabling the backlight later. So that's not something which is unavoidable. Okay, that's it. Then I will continue.
I would have a short question,
Yes.
especially on the Torizon core builder side. So can we directly start with implementing a custom panel driver with Torizon core builder?
Yes, that is possible. I also know from one customer who did it like that. So he was directly using Torizon core builder because he also said, I don't want to take care about kernel module compiling, and I just want to make it work. This works. It's just the iteration is normally a bit slower than if you do it directly. So if you have to debug, I normally prefer to use the approach with the BSP, the Octo BSP, and then just manually compiling the kernel module, while Torizon core builder first might seem faster, but then in the long run, it's a little bit slower because it has less flexibility.
Okay, makes sense. Thank you.
Then the last thing is some debugging techniques for displays when you can't make it work. One thing you have to make sure is that the MIPI DSI driver loads, because often you see that it just simply didn't load. You can check that with LSMod. Then with ModProbe, you can force probe it. If it doesn't work, then maybe your database is outdated. Then you can just run a debmod -a and try it again. And if it then loads, that should work afterwards. If it still fails, or say something like invalid symbols, then you might have compiled the kernel with a wrong config or even in the wrong version, because Linux can be quite picky when it comes to that. This is something that is avoidable with using Torizon core builder, for example, because they include automatically the right kernel modules. Then another technique would be to add to make sure that the probe is called. In my driver, I added a lot of debug messages which tell me where exactly I went through. that helps me to understand if the driver probes, because if it doesn't probe, that normally means you have a problem with the device tree or the device tree overlay. So maybe you have a wrong compatibility set, or you didn't use the right format. For that, you have to check or compare your device tree with the device tree of, for example, evaluation boards from NXP or from Texas Instruments, and see how they did it for other displays, and then you have to apply this idea to your device tree. This can sometimes be a little bit tricky, but it should be something that is possible, is doable, not possible, doable. Then when it probes, you might want to check if the resolution and the refresh rate is correct. So here I expect a full HD display with around 32 Hertz. So this seems right. Yeah, with that you can already figure out if you, for example, would see that the refresh rate is just 1 Hertz, then probably you have a problem with your pixel clock, and then you have to fix this one. The next thing is the DRAM frame buffer utility that I use a lot, because it can provide you the same information more or less as the mode test, but a little bit more compact. But what I normally often do is I just want to dump some random data to the display, and this you can do with like that. So you just say random data to the display. And why is this helpful? You should then normally see if the data is really going to the display, because if you do it twice, you should see some different images. And the other thing you should also see is, for example, an OLED display, if it works, but it doesn't show any value, just black screen, then you don't even see a backlight. And if you then dump some random data on it, then it turns on the pixels. This is not the case with old displays like LCDs, because there you anyways have a backlight. So this is then how it looks like. This is this random data showing. A little bit more advanced, you can also read back values from the display controller. MIPI DSI allows you to do that, and then you can just print them. This can be helpful to verify that the connections work and that you maybe wrote the right thing. So just to verify that that you can read back what you expect was written. You can instrument the DRAM framework. This is something you can do with DRAM debug. Here I just dump the state. This is 0x40. That would dump the state, which is the same information that also mod test gives you, but it is printed by the kernel in the kernel output. And you have much more options. So this is just 0x40, but you can find them in the kernel documentation. And with something else, if you search in the drivers, you can also find, and you find dynamic debugs like def_debug, debug. You can enable them during the din debug command line in U-boot. So you set it as Toradex argument that will then pass to the kernel, and the kernel then will print this dynamic debug message. So for example, bind, that you know, okay, it was binding, it could even bound a display and so on. But this is so you really have to read the source code of the kernel to figure out what you can enable and what you can expect from a driver. So yeah, that's it. Just some hints. Often some parts of the initialization sequence are missing in the datasheet, as I already told you. So for example, sleep out, display on, backlight on can be missing. This is something you then would have to figure out through the MIPI DSI controller, or to make pressure on the display manufacturer. If the display turns on but doesn't show anything, maybe try to play with the DSI modes. Maybe that helps. So try bulk modes, try other modes. Then the command mode can't be used by all drivers. So just use video mode, as also said earlier, because a lot of drivers don't implement the command mode properly. But luckily, you can also send data during the port phases, so this is not, there is a workaround for that. Yeah, so that's it. And in the description, I said we show some random data on the screen or random displays. So we already saw some random displays, but we can of course also output images. So that's the last thing here, showing the QR code to the web page if you want to find the repo, to the slides, and so on.
That's great. Thank you very much, Stefan. I think we could go right ahead with the questions some of our attendees have asked. So first one would be, I'll read it out loud. The old FBTFT device driver code has been completely removed from the kernel 5.4 onwards. What is the current status of the FB interface? Are users forced to use TinyDRM or Direct Rendering Manager, so DRM, graphics subsystem for small TFT displays, which would be such an overkill?
Yeah, I mean, so there should be, as far as I know, still be the option to do some emulation of the frame buffer interface, but it will then fall back to the DRM subsystem. So it's just an emulation layer, but you would still see FB. However, I wouldn't recommend you that because it's not really flexible. But if you have a look at this DRM frame buffer utility, because it's also on my GitHub page, basically here. No, yeah, here it's the post. You would see it's quite easy to achieve the same with a DRM with the DRM frame buffer as what you achieved with the frame buffer device before, because you just get to a frame buffer, and then you can throw any data you want onto the frame buffer. This is also how I use this. What I do in this DRM frame buffer. It's really a small utility, so the overhead is quite small. Maybe that helps you. But yeah, you cannot really rely anymore on the old DefFB interface, unfortunately.
All right, thank you. Next question, I found an interesting one, and it's concerning, I believe, display timings and VSync settings. So the question is, can driving the display with such wrong seconds damage the panel?
I wouldn't say no, it's impossible, but honestly, I never saw it that it happened. So what I sometimes see is that the displays, if you drive it with wrong timings, have some recovery time. So if you then power it off and on again, it might still have some strange effects or ghosting effects, but they disappear after keeping it turned off for maybe 1 minute or 2 minutes. As said, I think it shouldn't damage them normally, but it's not completely impossible. So yeah, but I never destroyed one with the timings. So and even with overclocking and underclocking, it just does strange effects, and it flickers or it shows the thing that it displays makes absolutely no sense. So
All right.
Don't be too afraid.
Yeah. So there's another question also regarding frequency, but in this case more about the frame rate. Your example shows the display running at 32 Hertz. Should this also work at higher rates, say 120 Hertz? And what issues are likely there? So if you would use, say, 120.
So this display should at least work with 60 Hertz. So this is something you should find in the display datasheet. What is the maximum refresh rate? The reason why I can only drive it with 32 Hertz is because my layout. So I made a display adapter myself, and I think that is not routed properly. So I have then some noise, and of course, then if I have a pixel clock which is too high, you see some strange effects. but the display itself, this one should also be possible to run at 60 Hertz. And there are others which would support 120 Hertz as well. That's also the display controller can do that. We have four lanes, with each lane with 2.5 gigabits per second. So you should even be able to drive a 4K display at, I think, 60 Hertz.
Perfect. Okay. So the next question is about the setup of one of our attendees. He's saying, I have this setup, SoC to DSI to serializer GMSL to output to a deserializer. And the serializer is considered like a bridge or a display panel. So that's the question out of the two, which it would be. So quickly to repeat, he's got his setup from SoC to DSI to serializer GMSL and then output to a deserializer.
Okay, yeah. So if I understand it, here. If I understand it correctly, if you look here, so you have the MIPI DSI bridge, and then from here you go to a MIPI DSI deserializer, and that one will then drive the display. This is it's a bit tricky. So in theory, because I mean this is exactly the same setup as it is here. However, it depends a bit on how it is implemented. Toradex also has some TI drivers which then just implement a bridge, and then you have just a normal panel driver at the end, which is using panel simple. So you would have another bridge, and then you use the panel simple driver to actually tell the kernel what resolution it needs to use, what pixel clock it needs to use, and that's how it works. But there you normally don't need to send any MIPI DSI data to the display controller because you configure it, for example, through I2C. So it depends on it really depends on the display or the converter chip you are using. But the final display, if it's a parallel RGB display, you can then use just the panel simple driver again, and you don't need to implement a MIPI DSI panel driver.
No.
Toradex has an example for exactly that setup, so that you can connect an LVDS display. So maybe you can have a look at that Toradex kernel repo.
Okay. So on to the next question, how and where to find the list of controllers or displays already supported by a particular kernel in general and or in particular for Verdin AM62?
Yeah, that is tricky, to be honest. So normally you have to check the following. So yeah, basically in this directory here, you can find all the drivers for panels that are already upstream. I mean, that same folder exists also for this particular Verdin device. And then you find panel, normally the display controller name, and then .c, for example, Cytronix ST7003.c, and then you can open that file, and then you see what compatibilities are in there. And based on them, you can then figure out if your display is already supported. But it is quite tricky sometimes, to be honest, yeah. Because sometimes the same display exists under different names, which is even more confusing. So you have one vendor which says it has this name, then the other vendor uses the exact same hardware, but it uses a different name. And yeah, this is really, really a pain at the moment. But maybe if you have a look at this panel driver here, you will also see it's not super hard to implement your own panel driver. So you can just try to adapt it and hopefully make it work.
Okay. So a further question would be, some new kernel versions don't support display if it still have the drivers. How to confirm the same? If they're the same is probably the question.
If you have a replacement of a display, that if it is still the same displays, yeah.
Exactly. If the driver is still, around and supporting the display on a newer kernel.
I mean, if it is upstream, then it will still be in there. So if the display panel driver is upstream once, then normally they keep it, so they don't throw it out. So you can again check this page and see if your panel is still in there. If it is in there, it should still be supported. However, if it is a replacement of the display, so you get a new display from the display manufacturer with a slightly different name, you would have to check the data sheets and compare, for example, the init sequence. Are they still the same? Are the timing information still the same? If this is the case, then most likely the panels are still compatible. If not, then yeah, you have to write yet another display driver.
Yeah, exactly. Actually, we just received another question a bit continuing on that. So if the driver is not available on upstream kernel and also not provided by driver, in that case, what will the steps to write the driver for the panel and how to test it?
Yeah, that would basically be what I try to show with this webinar, and it's also what this sample driver tries to address. So if you use this panel driver, you should see how I implemented the other displays, and then based on them, hopefully you can implement your own panel driver. You can just add it in the same file, even just because you already have, I think, 4 or 5 displays are supported by it, and then you would just have to add your own one.
All right. So there is another question here. MIPI DSI display, it's support only ARM-based device, or other host also can configure MIPI DSI displays? So if there's other architectures, I believe.
Yes. I'm not that familiar with x86, to be honest, and I would assume they could support it, but because they often have HDMI or DisplayPort or embedded DisplayPort, most likely it's tending more in that direction. So you have more powerful displays, which can often also do upscaling or downscaling. For RISC-V, for example, I'm pretty sure they will also support MIPI DSI at one point, or even now. I'm also not that familiar with it, but it's just a matter of if they add a display, a MIPI DSI bridge to the SoC, and because RISC-V uses quite a lot of peripherals which are similar to ARM, most likely they support MIPI DSI panels as well.
Yeah, probably with x86 also, due to historical reasons and why what the x86 is usually used for. As you said, probably mostly HDMI and display ports, right?
Yeah.
All right. Thank you. Now there's a bit of a different question. So what about Zephyr? Does this apply the same, or where should I look for examples running a 5-inch display 480 by 720? So if they're using Zephyr, do you have any experience there?
I'm not super experienced, but from what I read I think there are Zephyr chips out there which even support the video mode for MIPI DSI, but most of the time I assume they don't use the video mode but the command mode. So that means you have on the display itself, the display controller, you have again a frame buffer, and then you just use MIPI DSI to fill that frame buffer, and the display controller will drive the display, because that allows the display controller to drive the display, for example, at 60 Hertz, but the update rate is maybe only once per second. So you can lower the power consumption, you can lower the CPU load for driving that display. And then, of course, there are other Sapphire displays which don't rely on MIPI DSI at all, like SPI. I guess most of them use SPI. Yeah.
Okay, thank you very much. And that would conclude the webinar for today. So thank you very much, everybody that could join, and also thank you for asking the questions. And finally, biggest thank you to Stefan for attending and delivering such valuable information. So have a nice day, everyone, and thank you.
Thank you. Thank you for hosting it. Thanks a lot.